Hello everyone and welcome to Lesson 5. Today we're going to be going over particle motion for calculus. In case you're wondering what particle motion is, we're talking about, well, first of all, what's a particle? Imagine it like a speck of dust or a ball, and it's going left or right or up or down, or it's going in some direction. Pretty reminiscent of physics. As a matter of fact, for those of you taking the physics course this summer, you're going to notice some parallels between this lesson and Lesson 1, or Lesson 3? No, really just Lesson 1. Yeah, I would say Lesson 1. Anyways, with particle motion, we first need to talk about some of the terminology that we're going to be using. And the very first thing we're going to be talking about right out of the gate is higher order derivatives. Basically, up until this point, we've been just taking what we call the first derivative. The reason why I put emphasis on first is because you can take the second derivative, or the third derivative, or the fourth derivative. And the way you do that is just by continuing the rules of differentiation or derivatives and going down the list. And we'll be doing that a lot today, so I'll explain myself more there. But here, look at this, f double prime of x. That's what we call it, f double prime. For instance, the next value would be f triple prime. As a matter of fact, I'll write them out right here. You've got f of x, you've got f prime of x, you've got f double prime of x, you've got f triple prime of x potentially. And then after that, what do you think we're going to do? Because I'm not going to continue putting tally marks here. Any ideas on what we're going to do for the fourth derivative and onward? I would say the only logical guess, not the only, but the only two logical guesses I can think of from you guys is one, 4 tally marks anyway, or 2, they have Roman numeral 4. That's what I guessed when I was in your shoes. As it turns out, the correct answer of what calculus people do, math teachers do, is you literally, anything past the third derivative, you just put the 4 or the 5 or whatever in parentheses. And you may be wondering, why parentheses? Well, because if you remove the parentheses, then you're saying the fourth power. If you put the parentheses in, you're saying the fourth derivative. So that's the notation you would use. The good news is, today we're only going to be dealing with these 3. We're not going to be dealing with anything past that. Although theoretically you can keep going, it's fun. And then as far as the notation goes for these second derivatives, I mean this one's interesting. See this, d squared y over dx squared? If you remember, the first derivative like that would be dy dx. And then you have this weird notation like d squared y over dx squared. Why is it that they have to move the 2 in the numerator and denominator? In other words, I'm saying it would make a lot more sense if it was dy squared over dx squared, or if it was d squared y over d squared x. Like, this would make a lot more sense to me. However, for the same reason that we don't want to confuse this with something squared, like a function squared, that's what the d squared y over dx squared does, and we don't use this actually. This is a very unique signature of a second derivative as opposed to something squared. So that's why they write it this way. It looks funny. The good news is we're not even going to be using this today, really, but that's what that looks like for the second derivative. In other words, we're really going to be using f of x, f prime of x, and f double prime of x. And now when it comes to particle motion specifically, we're going to be using terms such as position, velocity, and acceleration that, again, you would see in a physics class. And the thing that I'm going to tell you right now is that if you get a positive answer, and this is going to be a theme for all day today, if you get a positive answer, then that's going to be right or up. In other words, the particle is moving to the right or it's moving up. We define that as positive. If you get a negative answer for any of these answers today, then we would say the particle is moving left or down. Okay? Either one of them. It depends on where it's moving. And we'll talk about that more later. And so with that, let's first talk about position. Position is easy because it's just the original function f of x. Although we don't really use f of x for position. We usually use x of t. It's the exact same thing. T is the x variable. X of t is the y variable. You'll get the hang of it after a while, but it is confusing at first, I'll admit. And then if I were to show you a particle on a number line with 0 as the center point, what I'm saying is anything to the left of 0 is either left or down, can also be down, and anything to the right of your 0 is either right or it is considered up. And so that's it for position. One more thing I just want to write here while we're still on the first page is if I go back up to the top here with what I was saying about the x prime, double prime, stuff like that, since we're primarily going to be dealing with x of t today, I just want to show you what this is going to look like. X of t is the original function, the position. X prime of t is going to be the first derivative, and x double prime of t is going to be the second derivative. So don't be surprised when I use this notation instead of f of x in today's lesson. So with that, let's go ahead and talk about what we're looking at here when it comes to x of t. Remember, x of t is the position. And here's an example of the graph sine t. Now let's look at an example. For the above position function, x of t equals sine t, find the position of the particle at t equals 3 pi over 4 and state whether the particle is to the left or the right of 0. So again, if I want position, that is the original function, x of t equals sine t. And if I want the position at t equals 3 pi over 4, that's exactly what I'm going to do. I'm going to do x of t at t equals 3 pi over 4. Just going to plug it into the function. And by the way, for notation purposes, the way you would write that, you would write it as x of 3 pi over 4. You put the 3 pi over 4 in parentheses, and then you actually plug it in for t. So the sine of 3 pi over 4. Now, just over an hour ago, I was dealing with my pre-calc / trig students, and what we were doing was the unit circle. They just discovered the unit circle for the first time. Yeah, I don't envy them either. But it's fresh in my mind what the sine of 3 pi over 4 is. Can someone from the audience tell me if they remember? Sine of 3 pi over 4.
Is it root 2 over 2?
Positive or negative?
Positive.
It is positive root 2 over 2. You are correct. And the reason why is because 3 pi over 4, that is quadrant 2, and sine is positive in quadrant 2. And of course, if you didn't know that for the sine, I'm not going to lie, sine, cosine, tangent, all that stuff is kind of important for calculus, but it's like not the most important thing in the world. What I mean by that is you can still potentially get a 5 on the AP exam even if you didn't know that. I would still recommend you do know the unit circle for sine, cosine, and tangent, but you don't have to. So anyways, we get root 2 over 2. That's our position. And since it's positive, we would say that's to the right of 0. To the right of 0. And there we go. That's the first one. Oh, and by the way, just to prove that we did this right, let's go ahead and look back up at this graph right here. And if you remember the sine graph, you'll know that one complete revolution happens right here at 2 pi. You cut it in half, you get pi. You cut it in half again, you get pi over 2. And the reason why I'm doing this is because where's 3 pi over 4? 3 pi over 4 is somewhere in between pi over 2 and pi. It's about here. And so then the point is going to be this point right here. That's your position. And as you can see, it's positive, so we would say to the right of the 0. Any questions? Okay. Next, we'll talk about velocity. Velocity in general is defined as the first derivative, x prime of t. And when we talk about velocity, we're talking about a rate of change. So if you remember, basically, if I want you to walk out of here knowing anything at all, I want you to know that the derivative in calculus is synonymous. It's the same thing as the slope, which we said before, or maybe not or is the right word. I'm going to say and the rate of change. A derivative is a rate of change. That's technically what a slope is. But slope is easier because we've been dealing with slopes since Algebra 1. Now, a rate of change, for instance, the rate of change of position is velocity. So when we find the first derivative of position, we're really finding the velocity, and that's what we're going to be doing now. So again, the same function. Here's sine of t, and here we go. For the above position function, x of t equals sine t. Part 1, find the functions or velocity function x prime of t, and 2, the velocity of the particle at t equals 3 pi over 4. So as I was saying earlier, if you want the velocity, you're going to take the derivative, x prime of t. Derivative of sine is, who can tell me?
Cosine?
It is cosine, thank you. So we got cosine t. So first of all, there's our velocity function. Derivative of sine is cosine. And now if you want to find the velocity at 3 pi over 4, then all we're going to do is plug in 3 pi over 4 in for t. And now we have to find the cosine of 3 pi over 4. I'm going to be doing that this time. It's negative root 2 over 2. There's our velocity right there. There's our velocity. And now I would say, hey, this is moving to the left because left is negative, and that's what we got, a negative answer. And what this looks like on the graph is if I scroll up to the graph and I look back at 3 pi over 4, which we remember is right here, 3 pi over 4. Remember, derivative is the slope. So if I take the slope of this line right there and I draw it good enough, then I see that the slope is going downward. In other words, we're moving to the left. Any questions on that one? Okay, fantastic. And then with that, we're going to go on to acceleration, which of course is going to be the second derivative. So for the second derivative, first of all, I'm going to write it as x double prime of t. And now let's talk about how we find the second derivative. This is going to be the first time we've ever done it. It's pretty underwhelming. And yet, for some reason, a lot of students have trouble with this, which always confuses me. Although, if you have to do the second derivative with like a product rule or a chain rule or a quotient rule, then yeah, it gets pretty annoying. But right now we're just doing some easy examples, so it's not that big of a deal. So what I'm saying is we've got x prime of t, we already said it was cosine t. If you want to find the second derivative, you just got to tell me the derivative of cosine. Can someone tell me the derivative of cosine?
Negative sign.
Negative sign. Thank you for remembering the negative. Yes, so we got negative sign here. And now if you plug in x double prime of 3 pi over 4, in other words, negative sine of 3 pi over 4. Remember, sine of 3 pi over 4 is root 2 over 2, but don't forget that negative sign out in the very front, so it really is negative root 2 over 2. And so there's my acceleration. Now, earlier I said that velocity, if it's negative, it means you're moving to the left or downward. What does it mean for a negative acceleration? Do we have any guesses from the audience?
Does that mean you're slowing down?
Slowing down is a good guess. As it turns out, it's more complicated than that, and it is related, but right now, I'm going to say negative acceleration right now means nothing. Don't worry about it. If it's positive or negative, that's great. We don't care right now. We'll care in about 15 minutes, but not yet. But thank you for the guess, because that's what I would have guessed as well. So anyways, we have displacement. Displacement is basically defined as a delta x. In other words, x of t minus x of 0. You can think of it as an x final minus x initial, or you can think of it as x2 minus x1. Oh, and remember, this is kind of backwards, right? Because our x of t function, these are really like the y values. We'd call them y values if it weren't for the fact that it's x of t now. So what I'm saying is displacement, also known as a change in position. You find your position at the final time, subtract from 0. I'll admit it's not always 0. Like for instance, they could say change in position from 1 second to 3 seconds. Then, in that case, it's not x of t minus x of 0. It would be x of 3 minus x of 1. And you don't have to write that down. I'm just giving an example. But if it doesn't say what time, then by default, we're using in reference to 0. And once again, we're saying negative displacement means to the left, and positive displacement means to the right. And that's what we're talking about. So in the next example, for the position function, x of t equals t squared plus 1, find the displacement at t equals 3. Again, very simple. We're doing x of 3 minus x of 0 because we're assuming 0 is the starting point, like you should. So all you need to do is plug in 3 into the original function and then subtract when you plug in 0 into the original function. Notice, displacement, no derivatives. This is just the original function. So then that's going to be 3 squared plus 1 minus the quantity 0 squared plus 1. 3 squared plus 1, that's 10, minus 0 squared plus 1, that's 1. 10 minus 1 is 9, and there we go. You're going to notice we don't really have any units in this class. If it was a physics class, we'd be dealing with units, but in calculus, you typically don't deal with units for whatever reason. So 9 is perfectly acceptable. Okay. Next, I give a little blurb about distance traveled. I don't know why I talk about it. I put a joke in there saying that you can talk to me about it, and I'll tell you if you're really interested. But for today, I'm just going to tell you to cross it out. We're not going to talk about distance traveled because honestly, it involves an integral, and we are not at integrals yet, and we'll only barely get to integrals at the very end of the summer, so we're not going to really talk about that today. The next equation we have is average velocity. This one is taken directly from my physics course, lesson 1, although we modify it with the right calculus terminology. Basically, average velocity is equal to this function right here. This function should look very familiar to you because it's identical to y2 minus y1 over x2 minus x1. It's the exact same thing. And so, again, with average, here's the confusing thing. Average velocity, I thought velocity has to be derivative, but not if it's average velocity. This is the original function. This is not the derivative. Okay? And it's purely because they have the word average in there, as opposed to just the word velocity. In other words, if I cross out this word average and just have velocity, now it's a derivative, but the word average is there, so you follow this formula that, of course, we'll memorize. But don't worry, because it's the Algebra 1 slope formula, which hopefully you know by now since this is a calculus course. And as an example, we have the next example. Position function, same good old x of t equals sine t. Find the average velocity over the interval, blah, 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 to 3 pi over 4. Show this corresponding secant line on the graph below. So first thing I'm going to do is I'm going to say, I'm going to write y2 minus y1 over x2 minus x1 because I know what that means and I will not mess up. So then y2 and y1, I have to plug in the values 0 and 3 pi over 4. So in other words, x of 0 is the sine of 0. That's going to be just 0. That's my y1. And then if I do x of 3 pi over 4, it's the same thing as the sine of 3 pi over 4. And we already answered that earlier today. It's root 2 over 2. And again, that's my y2. So plugging that in here, it's going to be root 2 over 2 minus 0 divided by x2 and x1. Those are my t values. Those are my 3 pi over 4 and 0. So it's got to be 3 pi over 4 minus 0. You'll notice that the minus zeros don't really make a difference, and you get root 2 over 2 divided by 3 pi over 4. Now this is incredibly messy, and yes, you can multiply by the reciprocal to start simplifying. In other words, we can write root 2 over 2 times 4 over 3 pi, and then that will ultimately reduce to the final answer because 4 cancels with that 2, leaving you with a 2 in the numerator. Your final answer is 2 root 2 over 3 pi, which is really gross, but in case you're curious, that's like about 0.3. I did it earlier in my calculator. And so what that means on the graph here, if I were to draw the secant line, which is what they want me to do, I would basically plot the point at 0, and I'd plot the point at 3 pi over 4, and then I would literally make a linear line to connect them. And you'd say, well that's not too bad, right? And I would say, of course not, because why do you think we were using the linear line formula from Algebra 1? It's because this average velocity is literally just a straight line with the slope formula. And in case you're wondering what this means in English, like why does this average velocity matter? It's like basically, if you're on a roller coaster, what we're saying is you could either take the black path or you could take the blue path. You start at the same point, you end at the same point, so your average velocity would be the same. Even though it looks like it's going different with these crazy paths, the average velocities would be the same. Any questions on that one? Nope. Okay, then we will continue. The next topic we are talking about is speed, which, by the way, we are flying through like a ton of different topics here. We've only got, I think, 3 more new topics to go, and I know I'm going fast, but there's like probably 10 things to memorize from today. And the good news is, well, not the good news. Let me just tell you what's probably going to happen. What's probably going to happen is we're going to get through 10 things you have to memorize. You're going to forget like 8 of them by the time the school starts. But again, the goal is not necessarily to remember everything. The goal is when you see it in school, the next time around, you'll say, I remember doing it in the summer. And then when your teacher, and here's the important part, when your teacher asks, hey Jimbo, how on earth are you so good at calculus already, and we're just doing it right now? You have to tell them, because I have the greatest tutor in the world, Dan the tutor, and he was tutoring kids for free over the summer. And of course I took advantage of that because I'm a conscientious student. And then the teacher will reach out to me, and we'll be best friends, and I will get all the business in the world, and I will be a billionaire. So that's the plan for me. Anyways, continuing. For the function, speed. Okay, so speed is basically the absolute value of velocity. In other words, let me write that down. Speed is the absolute value of velocity. And remember, velocity is just the first derivative. So for instance, if you get a negative answer for your derivative, just take the absolute value, make it positive, and there you go, you've got the speed. The classic example I give with speed is when you drive in your car, does it matter if you're driving north or south? Does your speedometer say 30 miles per hour or negative 30 miles per hour? No, your car will always say 30 miles per hour, and that's why your car has a speedometer, because it measures speed, and it's not a velocimometer, because it doesn't actually measure velocity, or else it could be negative. That wouldn't be good. That'd be confusing. So anyways, for the example, for the position function that we've been doing a million times, find the speed of the particle at t equals 3 pi over 4. So remember, x prime of t, the derivative, we have already done this a bunch of times. It's cosine t. If you look at 3 pi over 4, we already said it. We got, actually that's negative root 2 over 2, right, for the derivative. And so then all we got to do is say absolute value on that, and the speed is going to be root 2 over 2, positive. And there we go. There's our speed. Any questions there? Okay, great. Next we have average acceleration. Good news, average acceleration is extremely similar to average velocity. As you can see, it's x prime, so in other words, we're using the derivative, first derivative, or velocity, divided by time. That's the average acceleration. So that's the formula we're going to follow here. If you want me to tell you what it is, like y2 minus y1 over x2 minus x1, it is kind of like that, except instead of saying y2 minus y1, I would say y2 prime minus y1 prime. It's the first derivative. So with that, we're going to do the same thing with x of t equals sine t from 0 to 3 pi over 4. So what I would first recommend is finding the first derivative. We already did it. It's cosine of t. Then I would say x prime of 0, cosine of 0 is 1. Then we'd find x prime of 3 pi over 4. That's the cosine of 3 pi over 4, which is going to be negative root 2 over 2. And then if I want to find the average acceleration, I would say y2, which is the negative root 2 over 2 number, minus y1, which is the 1, divided by t2, 3 pi over 4, minus 0. Now, this one really cannot reduce as well as the last one. Like, you're going to get this, negative root 2 over 2 minus 1 over 3 pi over 4. And because of that minus 1 in the numerator, it's not going to easily take the reciprocal of the denominator and multiply. Like, that will technically work, but it's just so confusing. I'm fine with you keeping this as the final answer. This is fine. This is much harder to simplify than the last one we did. And in case you're wondering, this is a negative number, which means you have a negative average acceleration, which again, we're not talking about acceleration quite just yet. We might be talking about it on the next page. Nope, it's the page after that, whatever. So then that's it for this example. And now the next thing we're going to be talking about, and again, I know it's a lot being thrown at you at once, but just see what you can remember, and then that's what the homework is for. The next thing we're going to talk about is the direction of travel. Basically, if you have a positive first derivative, that's like a positive velocity. That's like a positive velocity. And when you have a positive velocity, we would say the particle is moving to the right or up. And again, a particle is just a piece of dust, a ball. It's anything that can move up, down, left, or right. And then for it to be moving left or down, we're saying that it's a negative velocity. So that's what it is for a particle to be moving left and right and up and down. And of course, we're going to be talking about direction changes. In other words, if you want to turn around, then what needs to happen is two things. Number one, in real life, if you want to turn around, you have to do two things, whether you know it or not. The first thing you have to do if you want to turn around is you have to stop. You have to stop moving. And what that basically means is setting the first derivative equal to 0. That is what stopping means. If you have the first derivative equal 0, then you stopped. If you want a direction change, this is step number one. Step one, first derivative equals 0. Okay, then step two is more confusing. You're going to make a number line test, okay? And you're going to put all those values, like let's just make up some values, 2, 4, whatever, and you put them on your number line. And then you have to test points on your number line using the first derivative to see whether the value is positive or negative. And if you have a sign change, then that means you switched directions. Let me write that down on another page because I ran out of room. If you have a sign change in that number line that I just made, so for instance in the example with 2 and 4, positive, negative, positive, we would say we changed signs at 2 and 4, so we changed directions at t equals 2 and 4. So that's what we're talking about with changing directions. Which actually has a lot to do with what we're going to be talking about next week. I think it's next week. I keep saying it. I think next week is critical points and first and second derivative test, which is my favorite lesson probably. But I don't know that. I thought particle motion. I thought today would be critical points, but it's not. Today's particle motion. Probably not my least favorite lesson, because lesson 1's my least favorite, even though you get to talk about limits and stuff. Limits are like the worst part of calculus, and you really know that once you get through the whole course. But this is my least favorite lesson because there's way too much stuff to cover. And it's not my fault. It's calculus's fault, honestly, because there's like way too much stuff to memorize. And potentially all of this stuff could show up on the AP exam, which is why we're even talking about it in the first place. Or not even the AP exam, it could just show up in your normal calculus class. So all of this is fair game. Anyways, for the next thing we're going to do is, for the position function x of t, find the values of t for which the function changes direction over the interval 0 to 2 pi. So, like we just said, this is a two-step process. Step 1, x prime of t equals cosine t, right? And we need to set that equal to 0 and solve for t. Can someone tell me how to solve for t here?
You have to figure out where on the unit circle cosine is at 0, and those points would be at pi over 2 and 3 pi.
Yes, so I'm not sure if that
And,
came
like,
through. Oh, go ahead.
Yeah, and then it's gonna be obviously because there's a period, it's gonna be every pi after it.
Yes. Okay, you're exactly right. Now, I'm not sure if that came over with the recording, so just to repeat what you said, basically, you have to take the arc cosine to both sides, you reference the unit circle, you ask yourself, where does cosine equal 0? And there's two values we're going to use, pi over 2 or 3 pi over 2. We do not deal with degrees in calculus anymore. It's purely radians. And that's because degrees are an arbitrary number made up by the Babylonians. Like, why is base 60 or 360 important? It's not. It's a made-up number. But humans, us in America, conceptualize things in degrees. We're going to be dealing with radians in this class all year, because that is actually concrete. That's not made up. Every circle has 2 pi radians. And if you don't know what that means, that's okay. But here's what I'm saying. We got pi over 2, 3 pi over 2. As you said, technically this goes on forever. You're going to get 5 pi over 2. You're going to get 7 pi over 2. But I don't count those. Why? Because I only wanted on the interval from 0 to 2 pi. So in other words, these are the two values that we're talking about here. Now notice I'm not circling these answers yet. Why not? because I didn't do step 2, which is to actually make a number line test. I need to make sure this switches direction. So here's pi over 2, here's 3 pi over 2. Actually, I don't like my number line because it goes on to infinity, or at least implies it goes on to infinity. I'm going to cap my number line off from 0 to 2 pi like this. This tells me that when I plug in values, I need to plug in values in between 0 and 2 pi. So first, I need to test a number between 0 and pi over 2. Let's choose pi over 4. And remember, I'm plugging in values into my first derivative, which is the cosine of t. So for instance, the cosine of pi over 4, that is positive root 2 over 2. I don't care about the root 2 over 2. I just care about the fact that it's positive. So for that reason, I'm putting a positive on my number line right there. The next value I have to choose has to be between pi over 2 and 3 pi over 2. I think a good choice would be pi. I know the cosine of pi is negative 1, which is negative. So that's there. And then lastly, a value between 3 pi over 2 and 2 pi. We can do 11 pi over 6 if we want to. That would be negative. No, cosine's positive because quadrant 4. Positive root 3 over 2. Positive in that last region. It looks like we do have sign changes. We have sign changes at both points at t equals pi over 2 and 3 pi over 2. And for that reason, that's our answer. Pi over 2 and 3 pi over 2. Now here's the question. What would it mean if, for instance, I had 2 positives in a row? Like let's say here, I draw another number line, and I have 2 positives in a row. Basically what this would mean is, imagine you're driving in a car, you're going forward, you come to a stop at a red light, and then you go forward again when it turns green. That's not changing direction, that's still going forward. So that's why that circumstance would not be turning around. Okay, and now finally, the last thing we're going to be talking about today before we do some example problems is speeding up versus slowing down. And it is a question of looking at velocity versus acceleration. Now here's what I made this very nice chart here with all the 4 circumstances you can have, and let me just put it very simply. If both are positive, which is what the first scenario is, it's speeding up. If one is positive and one is negative, which is both of these cases right here, that's when it's slowing down. And then the fourth case is again, well, not both positive, but they're both negative. If that happens, you're speeding up again. So basically what we just learned is that if you're speeding up, it means that it has the same sign. Velocity and acceleration have the same sign. So in other words, you can have a negative acceleration and still be speeding up, which is confusing, but it's true. Just imagine you're in a car and you slam on the accelerator going backwards, going the wrong way. You're speeding up, just not probably the way you want to go. And then if you want slowing down, then what that means is you must have opposite signs. You have opposite signs between your velocity and your acceleration. And with that, we look at one more example, and then finally we just do a grab bag, a potpourri, a mixture of all the different topics we talked about today, all in like 2 questions. But first, we have this one right here. Again, our favorite function in the world, x of t equals sine t, for the last time. Determine if the particle is speeding up or slowing down at t equals 3 pi over 4. First thing I do, let's find the first and second derivative, shall we? We know the first derivative is cosine t. We know the second derivative is negative sine t. Now we just have to plug in 3 pi over 4 for both. X prime of 3 pi over 4, like we said, that's negative root 2 over 2. And then x double prime of 3 pi over 4, that's going to be the exact same thing. It's also negative root 2 over 2. We did this earlier in the video. Now basically what I would say, they have the same sign. They are both negative. So for that reason, it's speeding up. It's speeding up in the negative direction, but still speeding up by definition. And that's it. That's all you have to do. Look at that. It gave us all this room. And even me with my size 50 handwriting was still able to fit it in this page. And that's basically it. So, oh, and in case you're curious, the exact same thing is true in physics. In physics, if you want to speed up or slow down, your velocity has to have the opposite sign as acceleration. And then the last page we have here is just a summary of everything we just talked about, all in one neat package. If I would recommend one thing to be most familiar with after today, it's the fact that position, velocity, and acceleration are the original function, then the first derivative, then the second derivative. If you can remember anything, please remember that. And with that, we go into some example problems. So, number 1, a particle I messed up. This is on 2 lines. I'm going to rewrite it on 1 line. A particle travels up and down along a path given by the function, and I'm going to rewrite it up here. X of t equals 1/3 t cubed minus 2t squared plus 3t minus 2, where x of t represents the particle's position. Find the following. We're going to first find the position at t equals 1. Remember, position is the original function. We are plugging in 1 for the original function. Wherever I see a t, I'm going to put a 1 there. So for instance, 1/3 times 1 cubed is still 1. So 1/3 times 1 is 1/3. Minus 2 times 1 squared, that's just minus 2. Plus 3 times 1, plus 3, and then minus 2. And so you can plug this in a calculator. You can get a common denominator. I'm assuming you know how to do this by now, but just to do it anyway. 1/3, negative 2 plus 3 minus 2, that's going to be minus 1. Get a common denominator of 3 over 3. It's going to be 1/3 minus 3/3. Final answer, negative 2/3. Any questions there? Okay. Next, velocity at t equals 1 and state its direction. So remember, velocity is going to be our first derivative. Hopefully you remember how to do the power rule. This is like 4 power rules in a row. So to help you out, the first one is going to be 1/3 times derivative of t cubed. Bring the 3 out in front. The 3 and the 1/3 cancel. That's very nice. And then times t to the now second power, because it goes down by 1. Okay, next derivative, minus 2t squared. Negative 2 times 2 is going to be minus 4, and then t, now to the first, but you don't have to write the first power because it's the same thing. Derivative of 3t is just plus 3, and then the derivative of minus 2 is 0. So in other words, our derivative is t squared minus 4t plus 3. And if we want the velocity at t equals 1, then all we got to do is plug in 1 for this velocity. It's going to be 1 squared minus 4 times 1 plus 3. Final answer, 0. Velocity is 0. And that says to state its direction. That's like a trick question because this thing's at rest. In other words, it's not moving. It's not moving left, not moving right, not moving up, not moving down. This thing's at rest. Next, acceleration at t equals 1. We remember that acceleration is the second derivative. So first I would rewrite my first derivative. It was t squared minus 4t plus 3. And then if we want the second derivative, just take the derivative again using the power rule. So bring the 2 out in front. It's 2t minus 4, because the derivative of 4t is just minus 4. And then derivative of plus 3 is 0, nothing. So it looks like then this is our second derivative. And then plugging in 1 for t, it's going to be 2 times 1 minus 4, which is negative 2. There's our acceleration. Next, part D. I believe we have more on the... Yeah, we have a part E on the back. That's exciting. But part D, average velocity over the interval from 0 to 1. Hopefully we remember what the average velocity formula was. Remember, it was, I'll call it V average, is equal to x of t2 minus x of t1 divided by t2 minus t1. Or in other words, it's just the algebra 1 slope formula for the original function. This is not a derivative. So in other words, I need to plug in 1 for t in the original function, which luckily I did that already. That was the answer to part A. Part A, I plugged in 1. And I got negative 2/3. So that's what goes in this first spot right there, negative 2/3. And then minus the same thing, but I need to plug in 0. Luckily, plugging in 0 here is really easy. You just get minus 2 at the end, because everything else turns to 0. So be careful there. It's minus negative 2. It will be plus. And then divide it by 1 minus 0. So it looks like we got negative 2/3 plus 2 over 1. Anything over 1 is the same thing. Get a common denominator of 3 over 3. Basically what you're going to get is you're going to get negative 2/3 plus 6/3, which means you'll get a final answer of 4/3. And that's our average velocity, 4/3. Any questions so far? Okay, now onto the next page, part E. Any direction changes for t greater than or equal to 0. Remember, we talked about direction changes. First thing you got to do is find the first derivative and set it equal to 0. We already found the first derivative. We said it was t squared minus 4t plus 3. Let's set that equal to 0 and start solving. So hopefully you remember how to solve a quadratic equation. You don't need the quadratic formula, you just need to factor. This is going to be t minus 3 times t minus 1. Okay. By the way, that's why we gave that pre-calculus review at the beginning of the summer. We had to make sure that you know how to factor. And so you're going to get 2 times here. You're going to get t equals 3 and positive 1. Remember, that's not enough on its own. Next thing we're going to do is we're going to make a number line. And this number line starts at 0 and will eventually go to infinity, sure. But all my number line is positive 1 and positive 3. And now I just need to plug in values in between each of these, and then we're going to be good to go. So first I'm going to plug in 1/2 in between 0 and 1. Now basically there's one of two things you can do here. One, you can plug into the first derivative, t squared minus 4t plus 3. 1/2 is obviously not ideal. It's kind of annoying. You get a lot of fractions. Here's what I'm going to recommend we do in the future. Use the factored form. Watch this. 1/2 minus 3 times 1/2 minus 1. I don't care what the number is. I don't care what the answer is. I just care that 1/2 minus 3 is a negative number, and 1/2 minus 1 is also a negative number. And a negative times a negative will give you a positive every time. In other words, anything between 0 and 1 will get me a positive answer. That's how I fill out my number line. Next, I need a number between 1 and 3. Obviously, 2 would be the best choice. So for 2, I do the exact same thing. I'm going to say 2 minus 3 times 2 minus 1, the factored form, just plugging in 2 for t. 2 minus 3 is negative 1, times 2 minus 1 is positive 1. Negative times a positive gets me a negative, so that's negative. And then I just need a number greater than 3. Let's say 4. I'll plug in 4. I can technically plug in 1 million if I want, but I'm not feeling that risky today. It's going to be 4 minus 3 times 4 minus 1. That's a positive times a positive. We will get a positive every time. And as you can see here, we get 2 direction changes because we have 2 sign changes. We have sign changes at t equals 1 and t equals 3. So therefore, there's our answers for this one. Any questions? Also, just a fun fact for today. This calculus course originally started in 2020 when me and my best friend from school, Josh Mack, who you don't know who that is, but basically him and I were both like really good at math in high school, and we came together and put this calculus course together. Now, since then, Josh got a job at, an engineering company, sorry. But now it's just Dan the Tutor. I guess it was still Dan the Tutor back in 2020. And really, I just hired him to get the help to make this course. Basically, Josh is the one who designed 90% of this course and the questions inside it. And of course, I looked over it and made sure it got the Dan the Tutor seal of approval. The reason why I bring up Josh Mack today is because just last weekend he got married. And so that's why I mentioned that. And I was at his wedding in Ohio. Terrible. 7 hours away. Never do that again. So anyways, with that, number 2. A particle travels up and down along a path given by the function x of t equals 1 over t plus 1, where x of t represents the particle's position. Find the following. First, we're going to find the position at t equals 1. Obviously, what's position? It's the original function, so I just need to plug in 1, and I get 1 over 1 plus 1 That's just going to be 1/2. Real easy. Next, we need to find the speed. Remember, speed is the absolute value of velocity. And velocity is the first derivative. So now we got to take the first derivative of this. If you remember, this is a quotient rule where, if you remember what I said, u is the numerator, so 1. V is the denominator, so t plus 1. U prime is going to be 0, and V prime is just going to be 1. Derivative of t plus 1 is just 1. And if you remember the derivative format, it's low d high minus high d low over bottom squared. And off we go. There's our formula. So now for the derivative, it's going to be v, which is quantity t plus 1, times u prime, which is just 0. That whole thing will go to 0, actually. And then minus u, which is 1, times v prime, which is 1, divided by v squared, which is quantity t plus 1 squared. So basically our derivative, x prime of t, simplifies to -1 in the numerator, and in the denominator, the quantity t plus 1 squared. Now all I need to do is plug in 1 here. So x prime of 1, plugging in 1, -1 over 1 plus 1 squared is 2 squared, so that's 4. Looks like the velocity is -1/4, but speed's the absolute value, so the speed is going to be +1/4. If it asked for velocity, then I would answer -1/4. Any questions there? Okay, now you're going to love me, because part C, we want to find the acceleration. Yeah, that's a second derivative, and the first derivative was really annoying, but that's okay, because I don't complain. And all I'm going to do is the exact same thing. U is equal to numerator -1, V is equal to the denominator, t plus 1 quantity squared. That means u prime is still 0, and v prime, I'm going to ask the audience, but first I'm going to give you a hint. It is a chain rule from last week. It's a rule inside another rule. Can someone tell me what the derivative will be? So remember, for chain rule, first I take the derivative of the outside. That's the power of 2. So I bring the 2 out in front, multiply it by t plus 1, now to the first power, not that that matters, and then times the derivative of the inside t plus 1. That derivative is just 1. So it looks like it's just 2t plus 2 after I distribute the 2's. And so that's actually not bad at all. So plugging in the formula, I'm going to get x double prime of t is equal to low d high, so t plus 1 quantity squared times 0. Yeah, that went to 0 again. That's kind of nice. And then minus u times v prime, so -1 times 2t plus 2, divided by the denominator squared, so that's t plus 1 squared, and then that squared. Wow. But we'll deal with that pretty easily. So I'm going to continue on the next sheet of paper for me. Basically what I'm going to say is that these two negatives right here make a positive, and anything times 0 is just 0. So in the numerator you have 2t plus 2, and in the denominator what I would say is that t plus 1 squared twice is actually t plus 1 now to the 4th power, because you multiply those exponents together. Property of exponents. And so now, since we want the second derivative when you plug in 1, all I'm going to do is plug in 1 here. 2 times 1 plus 2 over 1 plus 1 to the 4th. That's going to be numerator. That's going to be 4. Denominator, 2 to the 4th is 16. Looks like we get a final answer of 1/4 for the acceleration. Any questions there? Okay, we're almost done today. Just 3 more questions left. Displacement at t equals 1. Remember, displacement is just saying x of 1 minus x of 0. In other words, plug in 1 into the original function minus when you plug in 0 for the original function. And the good news is we already plugged in for 1. I believe that was part A. Yep, it was 1/2. So it's just going to be 1/2 minus, when you plug in 0 into this function, what do we get? Well, if you plug in 0, it's going to be 1 over 0 plus 1, which is just 1. So 1/2 minus 1 will get a displacement of -1/2. Not bad at all. Now for part E, we're going to find the average acceleration over the interval -1 to +1. Remember, average acceleration is going to be x prime of 1 minus x prime of 0. It's the first derivative, not the second derivative, even though it has acceleration in the name, divided by 1 minus 0. So again, the good news here is we already found x prime of 1. We did that back in part B. We got -1/4. Remember, absolute value is speed, but I don't want speed. I want the negative, okay? So it's -1/4 minus, when I plug in 0 for the first derivative, did we do that yet? Probably not. The first derivative was -1 over t plus 1 squared. So that means -1 over 0 plus 1 squared. Let's see, that's going to be -1/4. Double negative here makes it plus 1 over 1 squared. Yeah, that's just plus 1. So -1/4 plus 1, that's 3/4. And that's going to be our average acceleration. Any questions there? Oh, and just to explain, how did I get 3/4? Well, remember 1 is the same thing as 4/4. I did 4/4 minus 1/4 to get 3/4. A lot of kids hate fractions for some reason. In my opinion, they shouldn't be in calculus, but I don't get to decide that. And then finally, part F, last question of the night, is the particle speeding up or slowing down at t equals 1. Okay, so for speeding up or slowing down, all you gotta do is you gotta tell me the first derivative and the second derivative at 1. And again, we did this already. Like the first derivative from part B, we got -1/4. And then the second derivative from part C, we got +1/4. Because they're opposite signs, all we're going to say is it's slowing down, and that's all you need to say for that one. Oh man, that was a tough one. I'm not going to lie. There was a lot to go over there. But the good news is, if you'd call it good news, you have a very fun homework, and if fun's the right word for it. But seriously, you're going to be getting a lot better at this. And make sure you're not slipping with your derivatives. In other words, if you forget the power rule, if you forget your trig derivatives, then I don't even know how you're going to do next week's lesson. So if you want to review those lessons, it was like lesson 3 or lesson 4, where we went over derivatives and chain rule and product rule and quotient rule and all that fun stuff. And we're definitely going to be needing it next week and week 7 and week 8. So thank you all for attending. I hope you have a great rest of your night. If you have any questions, just stick around. I'll be happy to answer them. Take care, and bye-bye.